Thank you everybody for joining us today for our BJSS webinar as part of Leeds Digital Festival. Today's session, Engineering Insights, producing high performance code from static and dynamic languages with Andrew Bennett. We are recording today's session and we do want you to ask as many questions as you feel you want to using the Q&A functionality. So without further ado, I will hand over to Andrew for today's session.
Hi all. So yes, I'm Andrew Bennett, and I've been a dev here at BJSS for about the last 3 years, and I'm going to talk to you about how to produce high performance code from static and dynamic languages. So let's start. So first question I think we should just cover here: what are the most popular static languages that we currently use today? So obviously there's things like Java, there's C#, and there's Go. And obviously there's the kind of Java JVM variants like Kotlin, that sort of thing. The other thing, we've got things like Rust, and we've got things like C#. The talk today mainly is going to focus on Java and C# and Go, but the techniques we're going to show will also apply to toolchains for Rust, Kotlin, and C++. So again, the question says, what are the most popular dynamic languages? So we've got things like Ruby, things like JavaScript, and things like Python. Also things like Groovy, PHP, and Perl. Today we're mainly going to focus on the top three here, but again, techniques we'll talk about will apply to the bottom three as well. So I just want to talk to you about the difference between static and dynamic languages. So the first thing to say is that static languages is that at compile time that things are fairly fixed. Okay, so we know obviously the types that go into our function, and also at runtime we can't change what goes on the fields and methods. We can't change the functions at all. So at compile time, we basically know what's going to happen, and we can make code based on those assumptions. Some languages are different. So obviously things are untyped. So we use things like duck typing in dynamic languages. Duck typing. Sorry. So obviously, if method has a method, if the object we have has a method we want, we'll use it. But also you can change fields and methods at runtime, and so this sort of dynamicism we can see here it does give us performance problems which we have to try and solve, and we'll come on to that later on in the talk. So let's look at what this. So the first question is, what is a compiler? So a compiler basically takes a program, in this case written in C#, and converts it to a machine code basically. So that you do it in four main stages. So first things first, we have to verify the program we've written here basically matches the language we're writing it for. And then we have to convert that to a set of computation operations. Then we optimize those operations, and then we convert those to machine code. So that basically breaks down to these 5 stages. So checking the program is valid is done by syntax and semantic analysis. The computational operations is done by using an intermediate language. We optimize that intermediate language using some optimizations, and then finally, we generate machine code, which is done here. So look at these in a bit more detail. Syntax analysis basically is checking that the program itself follows the grammar of the programming language. Okay, so we do it in 2 stages. So we've got tokenization. So basically we take our source file, we break it up into elements, things like keywords, things like constants, things like variables. And then we apply some parsing rules to these tokens, these tokens, sorry. And if the parsing rules succeed, i.e. they match the elements, then we have a successful, the program is obviously valid, and we generate what's called a parse tree here. So on the right hand side here, we can see that we've got some tokenization definitions here. So constants obviously is a sequence of numbers, a variable is a sequence of letters, and we've got this expression here, which is this expression for adding, dividing, and multiplying constants and variables here. So this is an example of a parse tree using that expression. So a plus b times 2, and these obviously a and b are variables, and 2 is a constant. And obviously using that rule in the previous slide, we generate this particular parse tree that matches it, this expression parse tree here, as you can see. So next thing we do is semantic analysis. Just checking the meaning of the program is valid. So in English, we could say saying something like time flies like an arrow is syntactically correct, but not semantically correct. The time doesn't fly, obviously. So we do the same sort of checking here, and the key area of this is to do things like type checking, basically. So making sure that, for example, types passed to methods and functions are match, and the number and the variables passed to a function matches as well. We only do semantic analysis for static languages because it's mainly doing type checking, where obviously in dynamic languages we don't do type checking at all. And to do this, we use simple information, things like information on the variables that gets collected during the syntax analysis phase. So what we do next is we obviously, we've generated our parse tree, but then we convert that to what's called an abstract syntax tree, which is an AST. This is a simplified version of a parse tree, which looks something like this. And it's used in the next stages of the compiler. So you're basically just stripping out anything which has kind of come from the parsing to make it more like the program that's been originally written, basically. So next phase is to convert the AST into what's called an intermediate language. So intermediate language basically describes the program using a set of computational operations like load, stores, adds, multiply. So obviously before we were just describing it as how the program looked in terms of a source file. Here we're actually describing it in terms of operations that are actually going to be performed. So bytecode is a very popular intermediate language. So bytecode is effectively uses short operations that basically operate on the stack. A lot of toolchains use bytecode. So things you have like Java bytecode, you have Python bytecode, you've got JRuby in Ruby, and you've got CIL, which is the common intermediate language, which is used by C#. And the IL is generated from the abstract syntax tree by basically going through the subnodes and converting those into intermediate language. So this slide shows you some examples of bytecode. So for example, this shows you an expression A is equal to 10, B is equal to 5, and C is equal to A plus B times 2. And this is the bytecode that we get generated for Java. This is Java bytecode. And this on then the right-hand side, this is Python. This is Python bytecode. You can see that this is a stack-based set of operations. So obviously we push 10 on the stack. We store it in local slot number 1. We push 5 on the stack, push it in local slot number 2. We load back on top of the stack from these 2 local slots. We add those all together. We push 2 onto the stack. We multiply. And then we store that result in local slot number 3. Okay. And Python is very similar. So you're loading a constant of 10, you store it in local slot number A, and so forth, do an addition, and do the multiplication and return the result in local slot number 2, which is for the variable C. So next thing is, obviously we have our IL, now we want to optimize that to produce good code. So the first thing we can do is try to simplify expressions. So we do, so in this case, what we're trying to do is, so we do like constant propagation, and constant folding. The constant propagation will be the sense that let's say we had a program which was A is equal to 2 and B is equal to A plus A. In that sense, we can propagate the value of A to the expression B. So B would then become 2 plus 2. And then we can perform constant folding. So then B would then become 4, because obviously you can add 2 and 2 together and get 4. And that folds that expression down, so you get the value of 4. The other things we can do is improve performance. So we do things like loop unrolling. So instead of having a loop where we do a loop in our machine code, where we do a branch operation, what we can do is basically expand the loop out to do all the operations of the loop just multiple times. And that improves the branch penalty you get in CPUs. The other things you could do operator strength reduction. So instead of doing like multiplies and divides, you can do shifts and shifts those operations. The thing to say is obviously when we apply code optimizations, you apply an order, and what happens is you often get things like you get things where if you do have a set of operations, you end up with code that is either repeated, which you can remove, or code that's never used anymore and can be deleted and removed. So you do those two processes. And the final thing we do is register allocation. Registers on the processor are small, fast pieces of memory that you can access. There aren't very many, but what you want to is you want to try and utilize them as much as you can to do your operations. And there's techniques to work out which pieces of information should go into registers and how to deal with them when you want to move them in and out of registers and into memory. So in the final stages, obviously, now is to generate machine code. Now you've got two approaches. First thing is to do a ahead of time compilation, AOT, of your intermediate language directly to machine code straight away. This is what things like Go and C and C++ do. So you take a source file and you directly emit a binary object will contain your machine code. The other approach is to do is to what C# and Java do, is that basically you convert your program to bytecode and run that on the virtual machine. So what the interpreter does then is it basically sequentially runs the bytecode operations in order and performs the operations sorry. Then what it's also doing is it's profiling the operations it's doing. So it looks for functions it calls many times or regions of code it calls many times. And then if it finds that a region is called many times, it sends that to what's called a just-in-time compiler or a JIT. And what that JIT does, it takes the bytecode, it applies the compiler observation, the compiler observations we talked about on the previous slide, and generates your machine code. And the next time the interpreter hits that region of code, it will not interpret it, it'll actually run the machine code that's been generated and therefore improving performance. The problem with using JITs is they have a warm-up time. So they take time to get going, to get things going, to get working. So if you're doing serverless compute, for example, you have a cold start problem where it takes you time for your application to bring up. So technologies that are coming very recently are things like GraalVM and CoreRT, which basically compile the bytecode down to machine code for you directly. These techniques need to be able to see all the code that can be accessed from the main function. So if you're using like reflection, for example, you need to be able to define up front anything that via reflection you might want to do. So say you're doing DI, for example, the dependency injection, you have to list all the objects that the dependency injection would need to look for up front, so that you'll be able to that they'll be able to access them and actually generate machine code. So again, it's very similar in the sense that this is actually very similar to point one, but it's slightly different in the sense that it's not going from a source file to machine code, it actually is going from bytecode to machine code. Okay, so let's show you some demos. That's pretty enough theory. Let's have a look at some demos, what's going on. So first things first, I will show you C#, okay, how it works. So I've got a very simple program, which is my simple C# program. Notice I've got a set of operations here, which are doing some computation, but then we set the result C, but then we immediately override this C with this magic constant, which I'll come on to in a second while it's there. So what we're going to first want to do, I've got a script here, which will build our program and then using this IODISM command, disassemble it for us. So let's run that script. And this will show us, oh, sorry, right, this will show us, the, as you can see here, this is the bytecode instructions that have been generated for our method. You can see that it's very similar to the example we showed on the slide where we do some stack-based operations, but here is our magic constant. So it's put it in here, okay? So next thing, obviously, we'll run our program and typically this is run through the core CLR runtime and it uses the RYU JIT. So what I've written is I have got a script here that actually what we're going to do is we're going to override the core CLR runtime with a debug version of the RYU JIT so that we can see what goes on. We're going to tell it to disassemble the main method and let's see what happens. We run this script. So now we run this program. this is showing you the machine code instructions for that main method and what's happened. There's a bit of setup that's happened at the start of here. So this is kind of a prologue for our main method. But what you can notice here is obviously this is an instruction here with our magic constant. What it's done is the compiler has realized that the operations above that doing the additions and the to the variable C are not needed. So it's done dead code analysis, removed them, and just kept the result that this needs this magic constant, and then that's all that gets returned. This is really cool. So I talked about before is that obviously this has JITs have a startup cost. So what I've also Core RT is a technology that Microsoft kind of supports at the moment to do this. So I'll show you that quickly. What this does, it will. So I've got a script here. So this is going to build. So Core RT basically takes the bytecode that we saw on before and converts it to machine code. I'm going to build this. I'm going to run it. Going to run this. RT. We'll run this for both debug and release, and we'll see what happens. So let's look at the debug. Now, the reason why I have magic constants, I can find it in the code. What has gone on to sorry, my bad. Sorry, I need to quickly change the demo file to have this in. Sorry, I didn't include the actual compiler. That's what's wrong. Go back in. Let's run that again. Sorry. Right, this now works. Sorry. So we'll Core RT now. We'll take our bytecode and generate you. So it's going to use this. So CLang is a compiler toolchain that's primarily done for C and C++ work actually, but it's using that to generate us the native machine code. This will work just for a second. Right now, actually debug cool. Right. So this is now this to show you, this is the method that we talked about. Notice here debug Bennett is actually compiled all the operations that we're doing additions for C as well, but also here it's also done the operation of adding this magic constant and returning that back from a method. And just to show you where this actually gets called from, we can just jump back up the stack. This method gets called from here, and it goes and it gets called, and this actually gets called from manage main up here. Okay, so this is so this shows you that obviously it's run directly from the main method, so it's quite quick. Just to quickly show what happens when we do release and run release, and we run look for our constant again. So what's happening now in release mode? The compilers use the optimizations and realize that obviously the code above wasn't needed, and all we need to do is return that constant. Okay, and actually, if you look where this actually gets called from, we can see it actually gets called from manage main again up here. Okay, so let's go and look at Java. This shows you the Java. So what we've got here, we've got a very similar file for Java. Again, we've got a while loop here to get the JIT to kicking so it can loop. And we've got a very simple set of operations here. Just to say here is that obviously A and B are 2, so A plus B is 4. You're doing it 3 times, so C has the value of 12 at this point. And C will then in hex have the value of C, and I'll show why it's important in a second. So we're now going to let's build our class, run it. Okay, so this shows you that by decompiling that, this is the bytecode that gets generated. Again, very similar, lot of stack operations. So again, like we did for C#, sorry, I've added in this this library to decompile the bytecode. It comes out from the hotspot, which is the Java distro basically. So let's see what that does. So the when Java compiles code, it has two different jitters. There's a C1 and C2. C1 is a client-based jitter. It runs quickly, but doesn't generate it doesn't generate the most fastest machine code possible. But what we can see here, this is the result of compiling our method, but it's run to the C1 compiler to a jitter. Sorry, what we can see here is that we have the result C in here, but there's quite a lot of kind of stuff going on in the start of the function that we wouldn't mind removing to make it faster. So if you keep going on, what we'll see is that the C2 jitter kicks in later on. Optimizes again. This is the server JIT designed for server use. It runs more slowly, but it generates better code. And again, much smaller code, much smaller set of instructions. We're still returning back the value of C here, but obviously it's much smaller and much faster. Okay. I mentioned before about GraalVM. So I'm going to quickly show you this script for GraalVM. I'll give you a little bit about it while it starts up. So what we've got is a very different program for GraalVM. So again, we've got a magic constant, this one here. We've got this loop, so it basically it'll kick in basically and cause it to generate your machine code properly. So we're going to run the GraalVM script now. So what GraalVM as a project, it was done by Oracle Labs. It was a project to basically replace the JIT in Java with a JIT written in Java. And what that has allowed the Oracle team to do is to be able to obviously quite quickly add in new JITting techniques and compilation techniques and to improve code quality. And so one of the things that you could do with this is obviously just effectively give the bytecode we've got here and all the libraries that it needs to GraalVM. And GraalVM is obviously is looking at everything and running these compiler techniques, and then generates you a native image, which is what's used by things like Micronaut and Spring are bringing this in as well. So again, the concept problem I was talking about with serverless, you get a much faster startup when you're running your app in the cloud, for example. And unlike the Core RT, which is not really meant for production use, this can be used for production use, and it's it makes things much faster. And so let's just quickly look at what's been generated from here. What we can, sorry, I'll put them in. So again, we've used that magic constant to see what goes on. Right. So we can see that actually this is our main method. And if you get our main method, we can see that our magic constant is here. Okay, so obviously we are making a call to print to the screen here, but we are passing in this as an argument to that call here. So what you can basically see is obviously has generated to you code, and actually I can run this, and so that obviously will run much faster than obviously running it through a jitter. So that's Java. Let's quickly look at Go. So obviously Go goes from, so I've written a Go program here, sorry. Go obviously directly goes from the source file straight to machine code, and there's no bytecode in the middle. I've got a very simple Go script. Which run, so I've run that. We can see what comes out. Sorry, long. Okay. So the main is basically the main program where our code gets generated, and you can see on here we've got 3 calls to print them here. Okay, so we actually converted our source file directly to machine code straight away by running that Go command. So that talks about static languages. Let's quickly look at dynamic languages and how they get compiled. So this slide we saw before. The key point about dynamic languages is the fact that the structure of them changes at runtime basically. So methods and fields can change, and there's no typing going on. We use duck typing. So fortunately, to run code run dynamic code, you actually have to convert it to typed, something typed either in typed machine code or typed like Java or C# bytecode, and we have to have techniques to be able to allow us to do that. I'll talk about that in a second. The other thing is that because methods can change during the runtime of the program, we have to have caching techniques to allow us to quickly look at what the current location method is. I'll comment on that as well. So the first approach to dealing with dynamic languages is to basically interpret them, byte interpreter. So we write interpreter for the bytecode in C, for example, because it's quick, and we use C techniques and C tricks to make that really quick. And obviously we compile the interpreter to the machine we want to run our dynamic language on, and it's really fast. And this approach is used by things like CPython and Ruby. And obviously these still need caching techniques to improve constant method lookup. So to know where a method might be during a certain point when you run the program, we need to have a cache or hash to work out where the method basically is. So these are great, but they don't perform very well. There has been work, I know, to do a Ruby JIT, but I don't think at the current time it's as performant as the techniques that I'm going to cover in a second. So, so the other processes that have been going on are actually to write your compiler or toolchain in something like Java or C#. Okay. And why would you do that? Well, first thing is that it allows you to do what's called polyglot programming. You can basically call up Java code from Ruby, or you can call up, say, C# code from Python, for example, and vice versa, which is great. The real aim is to be able to use the virtual machine's JIT to improve performance. So obviously these have many man years work on them, like hotspots we had 25 years work on. You hope that by using the JIT you can gain better performance and then also just interpreting the code. So the way these compilers work is they will parse your dynamic program, generate an AST, and then we have to map that abstract syntax tree onto Java or C# bytecode libraries. And then you hope, and then you obviously would run it as if it was a real Java program or C# program. So there's a slight problem here. The problem is that dynamic programs that have typing in them, okay, so you don't have typing in a method, for example, but the problem is that to convert your application to represent your program, you have to convert it onto typed bytecode or typed internal libraries, because these are obviously written in static languages. And that's a problem we have to try and solve. And also we have this problem of the fact that where a method might be at a certain time in the program might change. So we need a way of having quick caching, we need to cache or work out where it is very quickly, because that obviously will impede performance if you don't. So how are we going to do that? So the first thing is mapping bytecode so IronPython and IronRuby make use of what's called the dynamic language runtime. This is DLR. So you convert your AST to an AST used by DLR, and that in turn could produce you CIL. So JSON and JRuby do it in a slightly different way. They basically bulk the AST tree they have, and they generate Java bytecode. And what they also do is they will do any typing conversions required to allow you to talk to the Java libraries. And I've got a demo to show what that means in a second. The other problem we have here is caching. So IronPython and IronRuby. So obviously when you call up a method, its location might change during the lifetime of the program. You might redefine it, for example. So we need a way of working out at what point in time what the method might be, where it is. So IronRuby and IronPython use this thing called the polymorphic caching feature. What you do is for every method that you hit, you assign a function that can dynamically change. So what you do is you record this method up, and you would ask it for where the location of where the method currently is, based on a particular set of types as well. And if it knows where it is, it will tell you where it is. If it doesn't, it asks DLR, where's my method for this particular set of types, and it will find it for you. And then DLR will then modify the code net method to match it and contain the location of the method for you. So we're actually changing the code of the function to match the new method. JSON JRuby uses a different technique called using the invoke dynamic bytecode instruction. So everywhere where a method call might be made, you put this in the invoke dynamic bytecode instruction. That is assigned a bootstrap method. A bootstrap method basically it returns back what's called a method handle, which has a set of operations to tell you where to find the method or constant. And these are quite quick and then optimized away by the JVM. And so what happens is that it runs its operations and it knows where to look for the method. And the next time you hit this instruction, it just uses the case of the method rather than invoking the invoke dynamic instruction. So let's show an example of JRuby, what's going on here. So, it's this one, sorry. Right, so I've got a test, I've got a Ruby, very simple Ruby program. Let's look at this. So again, you've got output method with no types, but we're going to call it up with two different types, integers and strings. So we're going to run our JRuby script. So we're going to run this program, we're going to run JRuby, we're going to tell it to use the invoke dynamic, but to tell us to, once it generates the AST for this, show us the bytecode that you would dynamically generate for this particular set of code that then allows you to mesh into the JRuby libraries and Java libraries. And I'll show it to you now. So we'd run this. And let's look at what I generated. So, okay, so what we've got down here. So, okay. Okay, so what we've got here is you've got this is our call to the output function. And these are the two parameters passed in, the first set of parameters passed in. You've got the two integers, 99 and 55. Now, the output function takes Java types into it. It takes in an IJRuby object. Now, to get that IJRuby object, we have to convert our data, the integers 99 and 55, to this Java type. To do that, we have to run the fixed-sum method, which is part of Ruby. So, but of course, this might be written by somebody, but this might be written basically. So to find out where the current location of it, we have to run this bootstrap method, which is obviously so we run this invoke dynamic instruction, which has this bootstrap method, which finds the current location of fixed num, runs it with 55, and generates you an IRuby object, which you can pass in to the output method here. But of course, obviously you need to do this again, but you need to have the strings you're passing in as well. So again, for strings, we're also going to put output, but obviously we need to pass in, we need to generate a Ruby string. For this, same principle, we define what the string method is, and the bootstrap method, find the bootstrap method, find what the string is, find it, pass these arguments, generate a Ruby string, and pass these two parameters down to the output method here, and then do the output operation. Okay. Okay, so that's great, and using JITs and JVMs are great, but the problem is that they're typically specialized to running static languages, and so certain bytecode sequences that you might generate for a dynamic language might not be optimized by the JIT. So a better approach here is to write your own JIT, which is specialized for a dynamic language, which obviously allows you greater control over what machine code you might generate and gets you high performance. However, we've got a problem. Machine code is static, okay? So the instructions themselves only work with particular data types. So like you might have to add an instruction which will only work with integers, but it won't work with strings, okay? And secondly is that machine code assumes that things are, that objects like data types are always in the same place in memory. They can't change their form, which is what happens in dynamic languages. So how are we going to map, how are we going to JIT a dynamic program to machine code? Well, what we do is that we interpret the bytecode we interpret the bytecode for our dynamic language, and what happens then is that we look for calls to a function which are of a particular type. Let's say we have in our case we had the output function, which it's always been called integer values into it. Then we tell a jitter, right, take the output function, specialize it to only work with integers, add guards and checks around it so that if you pass in something else into it, you'll basically de-optimize back to the interpreter and not use the machine code generator function, but then you will then use the interpreter again and use the bytecode to run your code. So let's show an example of Node.js doing that. So we have got a Node.js demo here. So basically, so Node itself, the V8 JIT is used by things like obviously Node.js and Chrome. So Ignition is the interpreter, and Turbofan is the JIT basically. This is a very simple JavaScript function we've got here. So we've got, it's very similar to what we had before. We've got a loop to get a JIT to kick in, and we've got output function which adds these together. And again, there's a typing involved, but what we hope is that the JIT will specialize this function to work with integers for us, because it's been called lots of times. So let's run this with this magic command. Actually, let's run the, sorry. Let's run that. So we'll run that, and we'll look at the output in a second. Right. Okay, so what happened? This is showing the bytecode that is generated for the output function. Again, it's not typed, and again, it's kind of a stack-based thing. Look below here, we can see the actual machine code that gets generated. For time reason, I'll be quite quick with this, but basically we do these are the optimization checks that happen. We're doing some check on the data coming in, and if it fails, we end up de-optimizing down, and we're hitting this lookup table. So we've got things like here, like I think not an integer here for reasons of de-optimize. Oh, you might have passed a string to this value, and we quit, and then we then call back into the interpreter and we interpret the call we would have done within the interpreter. The other thing to notice here is that this function has been specialized to work with integers because we have an add-l instruction here. So we're loading data in when we're doing an add-l instruction. So we know this function is specialized to work with integers, not to work with strings or any other data type. Okay. The final thing I want to cover is Truffle. So we talked about GraalVM before and how it's used for native image generation. Truffle is quite an interesting framework to do with dynamic. So it's used to allow you to run C, C++, Ruby, Python, R on a JVM. And there's also a library called Polygot, which allows you to do zero overhead interoperation between different languages as well, which is really cool. So, but what Truffle allows us to do is, the way Truffle basically works is we write what's called an AST interpreter for our language. So basically we write, to do that, we obviously we had the AST, the absent tree we showed before. So each node you can have, like an add or subtract or store node, we will write code to do the operation. And then obviously in that operation, we store the current state of what that node is doing. And obviously that code we write is in Java. And we add these annotations, these Truffle annotations to the code as well. And so what happens is we convert our AST into generate these AST nodes for our AST, and we run them. We run them in Java on the JIT. But we're using the GraalVM JIT at this point in time. So when the JIT tries to optimize the bytecode that is associated with these AST nodes, the GraalVM JIT actually knows that it's actually trying to, that these are AST nodes for, and it's Truffle. So it knows these are nodes derived from the annotations. And what it uses a technical partial evaluation. So it assumes the state of the nodes at that point in time won't change, makes an assumption. For example, it might say, I know that this method will always run with integers, for example, and it'll produce machine code based on those assumptions. Similar to what was happening with JavaScript, basically. That means you get really fast code generation. So this is currently being used for things like Python and Ruby, but it's still not production use yet. But some of the benchmarks showing that it's probably about it's at least 10 times faster, if not, than some of the other parts, some of the other Ruby techniques. So it's really interesting, and obviously the ability to do polyglot programming and the different approaches is also really exciting as well. So that kind of leaves my presentation for today. I have written some articles about this on the Engineering Insights page on BJSS if you're interested. And if you're, I also have the demos. I'm happy to share them to people if they're interested as well. So I think it's time to go back to Rich and to do some Q&A.
Yeah, brilliant. Thanks a lot for that, Andrew. Fascinating stuff. I've always wanted to know how JRuby worked under the bonnet, so that's really useful.
Thank you.
If anyone's got any questions, feel free to post them now, and I will ask Andrew them if they're appropriate, but I've got some others that I've been thinking about as well. So do you have any kind of standard benchmarking tools that you use for kind of assessing the performance of these languages, especially where they're not always just doing your simple examples that you've done, then they're sometimes maybe doing more complex operations?
That's a good question, actually. So I haven't actually, not for this talk, no. Although, so in my previous company, I have used benchmarking tools, but it was more for like embedded systems, and it was comparing compilers, C-based compilers basically, and see how they perform. But yeah, the problem with benchmarking tools is they're only as good as the benchmarks you use effectively. So you can get bias them as well. So it's quite interesting because even looking at some of the Ruby benchmarks that you see, they have to say, okay, well, it's doing like a certain set of operations, but it might show that it's great for JRuby, but it's only because it's JRuby has got work to optimize that away. So it's kind of a, I think from what I can see, sometimes there isn't, certain Java languages, there isn't the benchmarking tools there yet. I think they haven't matured enough. I think it probably is better for things like Java and C, which are more mature, but I think those benchmarking tools need to mature a bit more. But yeah.
Awesome, cool. And just on that similar vein, as you say, depends on the kind of operations it's doing. When you're dealing with a large amount of concurrency, for example, some languages tend to deal with that a lot more, naturally in the way that they run in their runtimes.
Yeah.
How have you found that when kind of looking at some of these tools, whether it be sort of the event loop in Node compared to doing sort of async or threads in Java, for example? How have you found that they compare in the sort of bytecode and machine code?
That's a good question, actually. So so obviously, it's something I haven't looked into decently, but you're right in the sense that the Java bytecode does have primitives to do synchronization, definitely, and atomics work, yes. Again, I know about this in terms of embedded systems. I've actually written atomic code for them, but for assembly. But it's an interesting area because obviously you're tying up, not only tying up the bytecode instructions to do the atomic instructions, but also you have to think about the threading framework under the hood as well. So things like how you utilize threads and threading pools are also quite useful and quite important as well. I think it's a balancing act, I think, between the bytecodes that get generated and the threading techniques that are used under the hood to talk to the OS as well. But it's something I would like to investigate, definitely. Yeah, it's quite interesting actually. So yeah,
cool, good stuff. And we're running out of time, so I've just got one last quick question. I've been playing a little bit with GraalVM, and I think the performance that you get out of it is incredible, and especially for finally there's something that can get fast cold starts in lambdas now in Java for Java. But I found the compiler super slow. It was really, really time consuming. Do you think that's just where it's at and we have to live with that, or do you think we're going to see that performance improve, or am I doing something wrong?
I think you're going to see that compiler getting better. I think Graal is a very new technology. It's only been in production for I think a couple of years, and I think the work has to go into make that better. But it's but as you say, it's an amazing piece of technology, and it's interesting what that feature gives to us, I think. But I think it just needs time to mature, I think, and for people to work with that. But definitely, it's very exciting. So yeah.
Brilliant. Well, thank you very much for a fascinating talk, and thank you to our participants who came along to view this talk. So thank you very much, and thanks for being part of Leeds Digital Festival. Did you have any closing comments, Karen?
So no, thank you, Andrew. That was really great. We've actually had some feedback that's come through just to say how much people have enjoyed it. So great work today. We will be sending out a copy of the recording, and obviously, actually, if Andrew's got any of the demos that he wants to share, we can send that out. And I hope everybody enjoys the rest of the festival, and we'll see you all soon.
Cool. Thank you, guys. Bye.
Thank you very much. Take care. Bye.
Bye.